In this presentation, I will talk about a specific class of biocomposites, that is natural textile reinforced mortar composites, also called natural TRMs. I will explain potential challenges and perspectives related to the use of this class of materials. So I will start by explaining the use of plant fibers in TRM systems, their mechanical behavior from a local to a global scale of analysis, and then investigate some technical solution to overcome the limitations related to the use of this kind of materials. A biocomposite is a material formed by a matrix that can be either organic or inorganic and reinforced by natural fibers, basically plant fiber or deriving from cellulose. The biocomposites market is increasing a lot in the last years with a compound annual growing rate estimated to be around 16%. They are used in many fields. They have many fields of application such as transportation, consumer goods, electronic and electrics. And a big share, or estimated to be around 24%, is related to the use in construction industry. That is the one that we are interested in this presentation. The reason why the interest in this class of material is ever increasing, it can be explained by means of this chart, in which on the x-axis we have the embodied energy, so the energy necessary to produce a material, and on y-axis is tensile strength. Materials are divided in several classes, and for instance, in green we can see those that are also defined green composites, let's say so plant-based composites. And if we compare this kind of material with similar material with industrial fibers such as glass fiber, CFRP, or carbon fiber, we can see that they do have a slightly lower strength, but we do gain a lot in terms of embodied energy. That means that to produce this class of green composites, we did much less. We have a much less carbon footprint with respect to more industrial materials. This is the reason why the interest in these materials is always increasing to respond to the sustainability requirements that we have more and more in these days. We have several kind of plant fibers that we can have in this class of materials, such as jute, sisal, hemp, flax, coir, kurawa. If we look at the main strength or mechanical properties of these fibers, for instance, by looking at flax and hemp, and comparing more traditional, for instance, carbon, the first thing that we can see is the high variability of values of plant fibers. This is because this kind of fibers are much less engineered compared to the others, so results are quite more variable. What we can observe in terms of strength, for instance, if you look at the maximum strength of flax is 2000 megapascal. This is more or less in the range of the order of magnitude of also high strength fibers. So we can see that there is a potential in terms of strength. In fact, plant fibers represented in 2012 the 15% of all the class of fiber adopted in composites. Nowadays this value is increased to 30%. Textile reinforced mortar are composites characterized by inorganic matrix, either lime or lime-based or cement-based matrix with the conventional high-strength fibers. Most used fiber are GFRP, glass, carbon, basalt, steel. What we can see from this chart that 6% of fibers are natural fibers adopted in the literature, but this value is increasing. These applications are increasing more and more. We can see that we can analyze this class of material on the composite scale, but also on the global scale. So with application on masonry elements, for instance, here we can see some application from the literature in which natural TRMs have been applied on masonry pillars or on masonry elements uniformly distributed on the surface or applied by means of strips. The first step to experimentally analyze this material is the composites manufacturing. This is a very crucial phase because in this case we have to try to reproduce on a local scale the behavior that this material will have on a global scale. This is quite difficult, and so to reproduce this is quite difficult, especially due to the flexibility of textile. So that raise a lot of issues and problems once we are applying within the fresh mortar. For this reason, I strongly recommend to stretch as much as possible the textile and to press by means of a roll, for instance, as shown in this picture, in order to guarantee the penetration of the textile within the matrix during the casting. The typical tests that we run for mechanical behavior are tensile test and shear bond test that are explained in detail in a recommendation of Rilem TC232. The very first step is the textile physical characterization. So the first challenge is to assess the cross-section of the textile because it is needed to analyze the materials in terms of stress. Here I'm suggesting two different methods. One is an indirect estimate that is based on the fact of estimating the density of these materials and then indirectly estimate the cross-section of the bundles. The other one is a direct measurement that can rely on, for instance, in this case on SEM microscope images and post-processing of the data. That can give us, once again, an assessment of the cross-section. If we look at the textile tensile response in terms of strain and stress, here I'm representing a typical response of natural fibers. In this specific case, it is flex fibers. We have an almost, let's say, almost linear behavior up to the root of the different bundles. A characteristic that is specific of plant fibers is they have small strain values, a lower stiffness. This is mainly due to two aspects. One is the distribution of the small fibers within the textile. So before having a contribution of all the fibers, we have a higher elongation. And the other, it's mainly due to a local, let's say, microscopic characteristic of these fibers that see the main components that are not directly aligned with the tensile direction, and this also contributes to this particular behavior. This behavior will have an effect also on the macroscopic behavior, mechanical behavior of the composites. In fact, if we look on the left, we have the response of a conventional TRM. This is basically characterized by a first linear behavior, then we have a transition phase in which the crack occurs, and then we have the third stage in which the response is mainly governed by the textile. If we look at the typical tensor response of, for instance, of a natural TRM, in this case flex TRM, we can recognize the three phases. However, the main difference that we can observe is that in the second stage, we have much significant drops in load due to the occurring of the cracks, and also deformations, the strains are quite larger. What we see is that still we can exploit the maximum strength of the textile with the rupture of the textile. And as I said before, this behavior is mainly related, of course, to the matter to textile bond properties, not to a not proper stretching of the textile during the installation, but basically mainly due to the typical tensile response of flex textile that we have observed before. This is let's say, a particular characteristic that I have experienced, but has been experienced by several studies in the literature, in which by using either flex or sisal, for instance, we can always observe this significant drop of load in the second stage and large deformations. I must say that also the nature of the textile has a significant impact of the mechanical response of the material. For instance, here we can see an example in which we have used both jute and flax fibers with a significant difference in tensile strength. And when we look at the tensile response of the composites, of course, in the case of jute that was weaker material, we have the occurrence on only one crack and much lower capacity of the entire composite, while in the case of flex, we have many cracks and we have higher capacity. So also the textile nature make an important is an important aspect. In this case, I must cite the Technical Committee 290, Rilem Technical Committee 290 AMC, in which in this framework, round-robin tests for mechanical characterization on natural TRMs has been running, and is of course still ongoing activity in order to analyze which is the influence, of course, of the type of the nature of the textile, but also the amount of textile that we are inserting in this material. Another fundamental aspect is more related to durability, because plant fibers embedded in either cement or lime-based matrices undergo through a degradation process due to the alkaline attack. We can see in this image which is the process. At first we have a degradation of lignin, then we have a degradation of hemicellulose, and then we have the break of this hemicellulose wall, and in the end we have a complete degradation of cellulose. This kind of degradation process is a well-known process. However, it is not easy to define the right protocol to use to simulate this degradation phenomena. For instance, if you look in this chart, we can find the response in terms of tensile strength of two different protocols. Both of them were simulating alkaline attack, alkaline environment on flex fibers, and then were accelerated degradation protocols of 55 degrees. In both cases, almost the entire mechanical strength was lost after 28 days. For instance, here we have some images at the microscope in which we can see the high damage on the fibers due to an alkaline environment and a complete degradation after 56 days. If we look instead at this other protocol in which fibers have been embedded in water for 1,000 hours, both water or seawater or alkaline environment, without increasing the temperature or ambient temperature conditions, in this case we recorded no degradation of the fibers. So we understand that it is the crucial aspect is to define the right aging protocol that can better simulate the right degradation phenomenon. Otherwise, we risk not to assess the exact degradation properties of the material. Also, another aspect is in the interaction between the fibers and the matrix. Here we can see, for instance, an image from the literature in which the wet drying process has created some breakage in the interface surface between the paste, cement paste in this case, and the fiber. In this case, I must cite again the Technical Committee 290 EMC, in which a durability aspect of textile reinforced mortar system is investigated, and one of the aim is exactly to reproduce, to assess, to set some aging protocols that can be adopted to analyze the mechanical properties of this kind of composites with the time. Here I'm also reporting some fiber treatments that can be applied to increase the durability capacity of plant fibers, such as alkaline treatment, hornification, mainly wet drying cycles, polymer impregnation, or hybrid treatments that implies more of these types. I will move now to the characterization, let's say, of the mechanical behavior of, on a global scale, so measuring elements externally reinforced by means of either one layer of a flux TRM system or two-layer flux TRM system. Specifically, this kind of experimental campaign regards walls that has been subjected to diagonal compression test. What we can observe here is the response of unreinforced wall. They are mainly characterized by a linear behavior up to the rupture, that is a fragile rupture, as expected. When we move to samples characterized by the one-layer flux TRM system, here we can see on the y-axis, of course, the load, and x-axis negative and positive displacement on the diagonal direction of the sample, we can see a much higher strength capacity and a higher also ductility of the system. And when we increase the rate of reinforcement with two layers of flex textile, uh, we do observe not only an increase of strength, but also an increase of capacity in the post-peak phase. In both reinforced cases, we can observe a significant drop of the load after the maximum capacity has been achieved, and this is, let's say, also due to the mechanical behavior on the local scale that we have seen of this composite that is characterized by a significant drop of load in tension. If we look at the results, especially related, in this case I am plotting the energy, and with the gamma 1 we have the energy in the elastic phase, gamma 2 the energy in the post-elastic phase. We can see that also, of course, the unreinforced wall have a abrupt and fragile behavior without ductility. We do have ductility in the second case of reinforced walls, and when we increase the amount of textile, we increase also this ductility of the system after the achievement of the peak. So this is to say that we do have a significant impact on the strength capacity of the wall once we apply these TRM composites, confirming their significant potential. In the last part of this presentation, I will show some improvement solutions to overcome the limitations we have seen. How we can improve somehow, the response of this material. And here we see, as I said, two different solutions. At first, textile impregnation. In this case, I'm relying on I'm showing an experimental campaign that has been carried out by using a polymer coating applied on the textile that has been dried in ventilated chamber for 24 hours at 38 degrees. And also we investigated the effect of matrix modification by using, in this case, by adding short Kurawa fibers, 1% in weight, within the matrix. These fibers have been also subjected before to a chemical and ratification process to increase their durability. And in this case, so also always on composites, on specimen to be carried out in tensile stress, tensile test, we assessed the effect of this flex textile impregnation, and also the flex textile impregnation plus the insertion of short Kurawa fibers within the matrix. Here, once again, we can show the strain stress response of the typical of the conventional flex TRM system. In this case, two textile layers has been adopted, and this is the classical response that we have explained before. Once we show the one in which impregnated textile have been adopted, we can observe that at first the maximum load is slightly lower. This may be probably related to the bond between the impregnated fibers and the matrix that can be a little bit lower. But what we observe that is significant is that the drop in loads that we have observed before are much less significant, and a significant denser crack pattern can be observed. And when we move to the samples in which, in addition to the impregnation of the fibers, we also have added some short fibers within the matrix, we can see that the crack pattern is much denser, and then also in this case quite significant output can be highlighted. For instance, the transition, the deformation at which we have the transition phase between the second phase and the third phase is much lower due to the impregnation, so to the increase of stiffness at lower strain values of the textile. And also by improving, let's say, the matrix, we can even increase the value of the stress within the composite in the second stage, so increasing a lot the overall response of the composites. In this case, in this chart, we can observe, for instance, the crack width with the strain development of in the three different series of sample. If you look at the red one, it's the reinforced one, so we have significant crack width. This is the average crack width. But if you look at the two improved composites which have impregnated the fibers and also used the short fibers in the matrix, we can observe an overall trend with much lower crack width. And we remember that we have to remind that this is a quite significant aspect if we look, for instance, at durability of the materials. Here I also have showing a book in which all this information can be found for those who are interested to deepen these topics. And so, as improvement solution, we have shown that by impregnating fibers or improving, let's say, the matrix response by means of short fibers, we can have an increase in the flexural strength of the matrix. We can improve the tensile behavior that is much more similar to the traditional response of TRM composites, and we can reduce the crack openings. I will move now to the conclusion. What we have seen with this presentation is that plant fibers have the potential to be used as reinforcement in NTRM composites due to their strength capacity, but of course the right amount of textile within the mortar should be assessed to have the best performance. We have seen the main challenges related mainly to the significant deformability of natural textile and to durability aspects. And what we see that there is the possibility to overcome this limitation, for instance, by means of textile treatments, that in this case we have shown how they can increase the mechanical behavior, the overall mechanical behavior of the composites, but as a perspective of the work, they can also be, also durability aspect can be also assessed and investigated to see if with these textile treatments all the limitations, all the challenges related to the use of this plant fabric in composite can be overcome. Okay, here you can find references I've cited during the presentation. Well, thank you for your kind attention. If you have any question, I will be glad to answer.